Hi everybody, so we're going to try another kind of modeling. In the last video we looked at perfect fractional crystallization. And going back to our MS Word document, that was this equation here. Now this equation assumes that as soon as we make a crystal, no matter how small, it's completely removed from the liquid. Never has contact with it. It does not equilibrate with the liquid. But of course, that's a very extreme case, and nature doesn't do that. What would be another way of thinking about a system? It could be that every time you form a crystal, it stays in contact with the liquid and continues to equilibrate with the liquid continually. So that's a type of crystallization that we call equilibrium crystallization, and that has a different kind of equation that's shown here. Now, the variables are all the same. We're going to apply this, like we did before, by calculating a liquid composition, a theoretical value. We'll have an initial magma composition, a melt fraction, and a bulk distribution coefficient. But with this new set of assumptions, that the crystals will now remain in contact with the liquid and continue to equilibrate, the relationships between these variables are a little bit different. So I'm going to scroll this upward so we can look at it. Now, what I want to do is build on what we've already done here. So in this modeling sheet, what I'm going to do is I'm going to make a copy. So for this sheet, I'm going to go to Edit, Sheet, Move or Copy Sheet, and I'm going to click Create a Copy, and I'm just going to move it to right after the modeling sheet. So it'll be modeling sheet number 2, and there it is. So that's the copy that I've made. Now this modeling sheet, the first one we did, involved fractional crystallization, so I'll call it FC. For this modeling sheet 2, it's going to be equilibrium crystallization, so I'll call it EC. Now, what I've done is I've saved all the work that we've done before. The curves that we created are still there, so those don't go away. And this allows me to save what I've done before, but now try something new. I'm going to get rid of all these equations here. So I'm going to go Edit, Clear All, because what I want to do is instead have not fractional crystallization, but rather equilibrium. I'll just call it EQ crystallization, since I'm having trouble typing it incorrectly. Now, this is going to require a similar kind of coding that we did before, except now, if we're going to take the example of silica, we have the original composition, our primitive liquid here, our starting composition C0, and that's going to be divided by the sum of F plus D star 1 minus F. And I think I forgot to add a parentheses at the end, so Excel is telling me to do so, and we'll just accept that correction. So here's our equation up here. Right? And again, if we have 100% liquid and no crystals, then our calculated liquid should be the same as the starting liquid, because it's the starting liquid after 0% crystallization. Nothing has happened yet. And we can do the same thing we've done before. If we allow for 10% crystallization, we'll have C0 divided by F plus D star 1 minus F, and we get this value here. But as we did before in the previous example, we don't want to type in this equation 80 or 100 different times. So instead what we're going to do is we're going to go back to this original equation and think about what we could fix. And I'll just give a negative example. If I just take this and fill it down without doing anything, then I get a bunch of crazy values. So let's take a look at what happened here. If I click on the formula bar here, it shows me what cells I'm referencing. Now, instead of referencing the initial composition here, it filled down, and now it's giving me this text value. Same thing here. This purple is supposed to be up here, and it moved. This is okay. I want to refer to that cell, but not to those. So I'm going to go back up to the cell, and as we did before, for the D value, which is over here, the D18, I'm going to put a $sign in front of the 18. So that means whenever we fill down, it means don't change the D. Excuse me, don't change the row 18, and there it is. Now I got to do the same thing for the original composition, D22. I want to refer to this cell here. When I fill down, I don't want the reference to the row 22 to change. And so now I can fill down, and I've got a new set of values. And again, we could do the fill right trick. If we fill right, we saw this before, if I fill right over in the titanium cell, I'm correctly calling out values for cells E18 and E22, but this red should be the melt fraction over here. So what I'm going to do is go back to the original cell and put a $sign in front of C26. It occurs twice in our equation, so I've got $2 signs to enter. So now I'll fill right, and then we'll fill down. And now we have a set of theoretical liquid compositions, but this time for equilibrium crystallization instead of fractional crystallization. So let's see what that looks like. Let's go take the magnesium and silicon values, we'll copy them, and we'll paste them into this chart here. So edit, paste special, new series, categories, next values. And we'll do the same thing we did before. For the markers, we'll make them hasher marks, and then we want a solid line. Then make the marker values much bigger so that we can see them. So this is interesting. The fractional crystallization model that we originally made does a good job of reaching these evolved compositions. The equilibrium crystallization model does not do very good at all. Now let's go back to this. Remember, in the earlier case for fractional crystallization, things really blew up at the very low melt fractions. So we could try putting in 0.01 and see if it works here. And it does. I'll make it 0.001. But it really doesn't get us that much closer to these evolved compositions. We could try different games with the mineral compositions. What if we have 50% silica instead of 30%? Does that help? It does a little bit. But look, while it explains these compositions, it still missed these, and it's not really trending towards those. So this is a way to just look at a different kind of modeling, and it looks like reality might be not exactly perfect fractional crystallization or equilibrium crystallization. I'll let you play some games with this and see if equilibrium crystallization can explain any of the other oxide trends. Don't spend a lot of time with it. If it looks like it's going to fail in most cases, then you'll probably have better luck and a more useful use of your time by looking at the fractional crystallization model. But we'll look at one more option in the next video.